All right. Well, again, thank you for the invitation and the opportunity to give some lectures here. Yeah, so please feel free to ask any questions and stop me anytime. That'd be great. Of course, but unfortunately, I cannot see everyone. So hopefully tomorrow be great if everyone's here. Yeah, so I'll talk about jet physics at both Lepton and Hadron Colliders. So that means in particular the Large Hadron Collider at CERN, where a lot of jet physics progress happened sort of over the last 10 years. But it's also relevant at lower energies, say the Electron Ion Collider in the future. And actually, we can even go to lower energies as soon as we have a couple of GeV, actually things start to look jet-like. And so we would like to make use of that, and I'll try to motivate why that's interesting. So let me start with an introduction, and then I'll have an outline sort of these 5 hours or 3 days of lectures. But let me start with a general introduction. This does not seem to work.
Oh, sorry. Try now.
Yeah. Okay. No, it works. No, it works. Okay, and of course, I'm not quite familiar with or I'm not sure how familiar you are with jet physics. So, you know, if it's too boring, or let me know, or if I should explain things in more detail, then also please let me know. Okay, so to start, and so you can still hear me from here, like this microphone works. Okay. All right, so let me start with the big picture, right? Eventually, you've probably seen this in other talks where I want to study matter at its most fundamental level. And that means that eventually, if you look at smaller and smaller distance scales, we're going to find quark and gluon degrees of freedom, as you can see here, which make up the properties of protons and neutrons, and all the way up to heavy nuclei. And so ideally, what we'd like to do is to have to use these fundamental degrees of freedom to describe experimental data, and then learn about the properties of these more heavy systems. And so, as it turns out, jets are like really an ideal tool to probe directly these say up and down quarks and gluons in experiments. They're really the best handle we have, sort of, that gives us a one-to-one correspondence between quark and gluon degrees of freedom and things that we can actually observe in experiment. But it's of course not only QCD where jets are going to be relevant, but it's really the entire standard model except for electrons, muons, and the photon. Everything else can actually also give us jets. So you can see here the standard model of particle physics. So we have the 6 quarks, then we have the neutrinos, and electron, muon, and tau. And except for the neutrino sector and electrons, muons, and photons, so really the electromagnetic sector, those parts are really not related to jet physics, but everything else is. So of course, the gluon up here, the force carrier of QCD, then the Z and W boson, and also the Higgs particle, they are relevant for jet physics, or jet physics is used to understand properties of these electroweak particles as well. Actually, that has been one of the main motivations at the LHC about 10 years ago to have to initiate an effort to understand jet physics better. That really started with the Higgs particle, where we can use that to understand different properties of the Higgs boson. So as it turns out here, also jets really play a very important role. And that's sort of what initiated a lot of the developments over the last 10 years. So the way to do this experimentally is, of course, through high energy collider experiments. The one with the highest energy, of course, is the Large Hadron Collider that you can see up here in Switzerland at CERN. That's really the highest energy that we have now, or they're currently restarting their program, and it's going to go now up to 14 TeV, versus before it was up to 13, and it's going to have higher luminosity, and all these 4 experiments are going to be upgraded. So we'll have a very precise and high luminosity measurement at the LHC, and here jet physics is of course going to be very relevant because it's at high energies. But it's really not just high energies. Also, if we're at low energies, say at the relativistic heavy ion collider at Brookhaven, which has up to 400 GeV center of mass energy, or the EIC in about 10 years from now, which will go, will have center of mass energies between 20 and up to 140. Also here, as it turns out, jet physics is going to be very relevant. But a lot, of course, of the developments were really coming here from the LHC, and in sort of more recent years, people have then figured out sort of what the connection is also to these low energy experiments. And of course, also at Jefferson Lab and at Bell, and I guess Anselm will talk more about this in the afternoon. Also there, of course, we'll have jet physics. At Bell, we're around center of mass energy of about 10 GeV. And also there, the final state looks jet-like, and you can do jet measurements. And they're actually very complementary to the measurements you would do at the Large Hadron Collider, even though they can be up to multiple TeV. So one jet can have up to, say, 4 or 5 TeV. It's just a single jet in terms of energy. At Bell, of course, going to be much less energy. But of course, you want to understand, can QCD predict these differences, right, between, say, 5 GeV and 5 TeV? Can we actually make that connection and do that in a quantitative way? So having this whole range of energies is really very useful and makes it really very interesting and challenging from a QCD perspective. Now, unfortunately, there was supposed to be a video on the next slide, but this is a PDF, so unfortunately that didn't work. But the nice images, of course, to illustrate what's happening these collider experiments is coming from CERN. You can see here the beam pipeline in the tunnel, which is a 27-kilometer long ring, maybe 200 meters underground. And so what you do is you accelerate protons to very high energies, and then you bring those to collisions at these kind of intersection points, where there's 4 experiments. One of those you can see here, which is the Atlas experiment. And so you accelerate those to a center mass energy of 14 TeV, and then you basically record what happens in these kind of collisions. And yeah, so that's where the video was supposed to be. So unfortunately, I can't show that.
Do you want to move the other one?
The keynote doesn't work, right?
Yeah.
That's the problem. So maybe let me show at least those images and then go back a little bit. So what you see in these collider events can look something like this. So we have 2 illustrations here from the CMS experiment. The first one shows basically a dijet event. So you have the beam going in this way, and then transverse to the beam direction, you have these 2 jets coming out. We can see that they were drawing 2 cones around this dijet event. And so what that means is basically that there's a lot of energy contained specifically in the cone that they've drawn, as opposed to, say, the radiation being more symmetrically distributed in the final state. And here in the lower one, you can see that we not only have these dijet events, that's something that's, for example, we also easily can have at E+ or minus collisions, but we also have these events where there's, say, 10 jets or so that are produced in a single collision in these kind of events. And so let me maybe go back a little bit. So this was supposed to be the end of the video, where, it's a little difficult to see because it has a lot of colors and would be easier to see with a video. But what you can see is here again, in the center, you have the main interaction point. And then you see different parts of the detector that light up, and they basically measure different particles. So they measure pions and muons and everything. And also here you can see that there's 2 cones drawn around dominant flow of energy. So one going up to the left here, the other one going down, and you see basically different parts of the detector that are highlighted here. And that basically means there's a lot of energy deposited in that particular direction. And it's not kind of spherically symmetrically distributed in the final state. And maybe there's a 3rd jet also over here where there's a lot of energy in a particular direction. And so, of course, ideally what we'd like to do is just measure quarks and gluons, but we can't actually measure those in the detector. And so the next best thing that we have are these jets. And the reason for that is that to first approximation, and I'll make that more quantitative later, but to first approximation, all these jets that we see here they originate from a quark or a gluon, or say a Z or a W or a Higgs boson. So there's one-to-one correspondence between quarks and gluons, so the type of things that we have in the QCD Lagrangian, and things that we actually measure in experiment. And so that's what I'm trying to illustrate here. So this jet here, say, originates from a quark, and it basically then emits a lot of particles nearly collinear to its initial direction. Or the lower one here has a gluon line. I'm trying to illustrate it that way, meaning this jet, say, comes from a gluon that then emits a lot of particles, and all of those particles that are created in this kind of parton cascade are contained in the jet that is found here. And so this one-to-one correspondence is what makes jets so interesting. We want to study quark and gluon degrees of freedom, and jets are basically the way to do that, to basically have this window to these very short-lived quantum processes. And of course, we need to make this more quantitative so we can actually compare to data. Okay, so a few words about sort of where this is coming from historically. And I have both one experimental paper and a theory paper. The experimental paper is shown here. It's from 1975, so it's really quite some time ago that jet physics kind of started. This is also an illustration from the Tasso experiment, where you're looking basically into the beam direction, and then you see these two sprays of particles coming out. The first experiment that basically claimed kind of this discovery of jets is, as I went from 1975. And what I'm trying to highlight here in the abstract is that this was, well, it was an E+E- experiment, like the one shown here on the right. And it was run at a center of mass energy of 6 to 7 GeV. So it's really low energies where they found these jets. Of course, now we're talking about TeV at the LHC, but back then, like 6 or 7 was already very good. And apparently here, by looking at the angular distributions, they could figure out that the events that you see look more like jets, like illustrated here on the left, as opposed to these kind of spherically symmetric distributions. Of course, they're not going to have that many particles in every single event. What they were basically just able to show is that if you average over many events, eventually you find that the events are more consistent with this topology on the left that looks jet-like, that has these two preferred directions, as opposed to being completely random and symmetric. So that was kind of the beginning of jet physics, and I think it was an experiment at Berkeley and Stanford in the 70s. So this was 75, and then there was a theory paper by George Sturman and Steve Weinberg that appeared just 2 years later, 1977, where they did the first next to leading order calculation of a jet. And not only did they do like this calculation, but they also basically wrote down the first algorithm to actually identify what it means to have a jet. Of course, what we need is something that tells us how many jets there are. So in this case, it seems kind of obvious that there are two jets. Here it's also kind of obvious, but as you saw before, say if we go back to the LHC, you see that there's a lot of particles that come out in these events, and here they've drawn and kind of conveniently already 10 cones around it. But in general, you don't know exactly, or at least without an exact definition or a precise definition, you don't know exactly where to put those cones and what exactly to call a jet. And so what they did in this paper for the first time is to actually have an algorithm that works for the experimental side and that works for the theory side to do a measurement of jets and to count how many jet events do we have. And also to then do a theory calculation, and one can then compare to this. And so we'll get back to this, to their particular algorithm later on. It's a very simple algorithm where it's, one can do theory calculations. And it's actually still of theoretical interest today, even though at the LHC we're not, or also at the EIC we'll probably not use that kind of algorithm. But it has a lot of interesting properties nevertheless. And so, for example, in soft Klein effective theory, people work still on that algorithm and try to understand its properties. And if you go to, they did in particular an NLO calculation in perturbative QCD, but if you go to higher orders in perturbation theory, then it gets more and more complicated. And so that's still really a challenge today. Okay, so that's basically what jet physics is coming from the 70s. But of course, it has evolved a lot since then. And so I wanted to give a little bit of an overview of where jet physics is relevant today. So the first one is, of course, that jets are just inherently interesting objects that allow us to study various aspects of quantum field theory in great detail. As I already mentioned, right, they can span energies of multiple TeV down to a few GeV. And so if there's anything in particular that we want to study, any aspect of quantum field theory, then they basically are a great tool or a great testing ground to actually do that. And so that's basically why, in general, people think about jets. But of course, they're not just inherently interesting, but they're also used for a lot of different things, sort of as a tool to study QCD, to study the standard model, as I already mentioned, and also to search for physics beyond the standard model. So for example, I'll show later some examples where you look at extensions of the standard model, where you search, for example, Z prime and W prime particles that are extensions of, or within certain extensions of the standard model. Then jets are basically an ideal tool to study that. And I'll talk more about this later on. Also, if you're interested, for example, in PDFs, or if you're interested in a strong coupling constant, all those things can be done with jets and with jet substructure. Then in addition to that, of course, you want to understand things like hadron structure. So for example, if we're at the EIC, where we want to study how the proton looks like in terms of its quark gluon component, we want to understand how these composite objects, these heavy nuclei look like. And of course, we're also interested in, say, the quark gluon plasma and heavy ion collisions. So you basically have this phase diagram over here, where if we're at zero temperature, that's typically what we have in proton-proton collisions or in electron-proton collisions. But if you study heavy ion collisions, then you generally in a region of finite temperature or in finite net baryon density. And so also in this case, in heavy ion collisions, you produce both the quark gluon plasma that you want to study, and then these jets are basically a probe of the quark gluon plasma that are also produced in these type of collisions. And it's very similar to the EIC, where you want to study cold nuclear matter effects. If you produce a jet that goes through, in case of the quark gluon plasma, it's hot nuclear matter. In the EIC, it's cold nuclear matter. But in both cases, you have a jet that goes through this nuclear matter, and by then studying the properties of the jets, they basically carry an imprint of the nuclear matter, and we can study that. Of course, the quark gluon plasma is then related to the early universe, where we expect that this quark gluon plasma has existed shortly after the Big Bang. And so by studying that, jets also really can help us a lot in this direction. And of course, by understanding all these things better, eventually what we want to understand also things like dark matter, as I already mentioned, or any sort of beyond the standard model physics. And we're coming back to the EIC. This is really a new component of the EIC science program. I'll say a bit more about that later, because it's relatively low energies. And so when the EIC white paper was written, there was really no jet physics included. But now in the EIC yellow report, there's actually quite a lot of jet physics in it. And that really changed because of all this progress that happened, that we understand much better now how to actually compute jet cross sections. And so now they're really an important component of the future EIC as well. And lastly, what I also want to mention, even though I'm not really going to talk about this, except for maybe very briefly toward the end, it actually seems that jet physics can teach us also something about hadronization. So if you think of a jet where they have these cones, and if you basically take the limit of the cone going to zero, then you basically end up just with a single hadron in every jet. And it seems like, even though that's still some ongoing, or that requires more work, it seems that jet physics actually tells us something new about parton-hadron duality and the need of fragmentation function, or maybe that we don't need fragmentation function to actually describe hadron production in the final state. So it seems also here, jet physics has sort of been a missing piece in our understanding of hadronization, and is sort of then also the starting point to understand, for example, more non-perturbative components as well. And we sort of have to make sure that first we understand the perturbative part. So I'll talk about this very briefly toward the end, but it's, I think, also a very interesting aspect that sort of connects to lower energy physics as well. And then it kind of seems that maybe we have sort of missed some of the things in the past, and it turns out jet physics was the missing component. Okay. Now, what you can see here in the lower figure is again a two-jet event. What I'm trying to illustrate here is that these jets really come in all kinds of shapes and forms. So one of the things we want to study is not only how many jets do we find and what's their energy, but we would like to also study what is like the internal structure. So it's like illustrated here, where you want to study what is called jet substructure, meaning that we want to characterize the radiation pattern that is inside these jets. So some of them, as you can see here in this example on the right, the jet on the right basically just has a single hotspot at the very core of the jet. So all the energy that is contained in this orange cone is really at the center of the jet, versus there's almost no radiation or no particles really close to the edges of that jet, or of this orange cone. And that's a very characteristic feature of some of the jets that you find at the LHC or at RIC or at the EIC, is that they're really very narrow. So if you draw a cone around it, it's very likely that all the energy is contained really at the core of the jet, and the outside of these jets is kind of empty. But that's not always the case. So what you can see here on the left is actually a very different type of jet. And so you can see here, especially with the green part of the detector, you can see that there's kind of two hotspots in the jet. So it has like a two-pronged structure, and it has basically almost nothing here in the center of the jet. So it somehow looks very different, even though both have, you know, probably very similar total energy or total transverse momentum relative to the beam. Their internal structure looks totally different. And one of the reasons, or I mean, of course, it has to do this on it has to average over events, but this difference here, that this is more like a one-prong and this is a two-prong structure, is that the left one could have originated from a Higgs particle, where, and I'll talk more about this later, where basically all the decay products of the Higgs are merged into a single jet.
Excuse me.
Yep.
So yeah, just a suggestion, like instead of pointing to the projector screen, could you point on the computer screen? Like it's kind of difficult to see it when you're pointing there.
I should
Can you
point here.
repeat?
Yeah.
Okay.
Yeah, like could you,
Okay,
can hear.
sure. I can do that.
yeah. Thank you.
Right.
And there is also, since you're getting interrupted, there is also a question from PV.
Sure.
If,
Yeah, I guess, can you just, maybe I missed this in the beginning, but one jet correlates to a particle, even if it is like the decay products in the particle. Can I think of it like that?
Right. So you basically think of it as, say, like a quark or a gluon, or say in this case a Higgs, that is produced here at very short distances. And then the Higgs basically decays, or the quark or the gluon emits a lot of particles, and they're going to be contained, or they basically lead to a spray of particles, right? And they're all contained here in sort of this radiation pattern that's contained here in the cone. I'll talk more about this later. So hopefully this will be more clear later on. But yeah, so you're basically trying to make a connection of the particles that you see in the detector, and you draw a cone around it, and then you hope that sort of all the radiation, you know, together. Maybe I should point at this here, right? That all the radiation taken together, that basically reflects to something that happened here at very small distances at very high energies, right? So that.
Okay, so you need both.
Sorry.
Sorry.
Hmm,
So you
go
need
ahead.
both sets of cones in order to understand that it was a Higgs. Is that correct? In this specific
Sorry,
image?
I didn't quite get the first part. Could you say again?
Sorry, you need both cones in order to understand, like both of the jets that we see right here, both of these orange cones, to understand that it was a Higgs at some point.
Right. So you cannot decide this really on an event by event basis, right? But you would have to basically event average And then you see that, for example, there are jets produced with a, basically what happens is that you have like a Higgs would produce a jet like this, right? But there are other processes that could also produce a jet like that. And so you basically have an average over all events. And if you see, for example, an increased number of events that produce these type of jets, then you can say event average that there, you see, for example, a peak in the mass distribution. And so you cannot say really on an event by event basis, right? Because you don't know if that jet really originated from a Higgs or if it was something else, maybe like a background process. But event average, you can eventually say what it is, and you get a peak in the distribution. I'll have plots for that also later on, where we basically look at the mass of a jet, and then you can see peaks in the distribution.
Cool. Okay, thank you.
Makes sense. Okay, so we'll get back to that more later. I just wanted to sort of mention where these things are coming from or why it's interesting, and then we'll make this more quantitative later, how to exactly actually do this. Okay, thanks. All right. Oops. Okay.
I have one more question before we move on.
Yeah.
Sorry.
There is also Alex. They have another question.
Another question? Yes, please.
Thank you. I'm just wondering, what is the typical divergence of these cones, and does it look like an approximately Gaussian distribution inside that? You said that it's more concentrated in the middle.
No, is it possible to make this a little louder?
Yeah.
We have kind of
Yeah.
trouble,
Yeah.
or is it
No, we can increase the volume.
or different speaker or something?
Because,
Okay, thanks. One moment.
it's 100%.
It's 100%. Okay.
Yeah.
Okay. Yeah.
Try to speak
Sorry,
louder.
I can try to speak more clearly. Is that better?
Yeah. Very good.
Thank you. Can you just tell us what is the typical divergence of these jets? And you said that it's more concentrated in the middle, but is that like a Gaussian distribution?
What do you mean by the divergence?
The divergence angle.
Oh, you mean the opening angle?
Yes, I think those are equivalent in this context.
Right. So I'll get back to that also later. So it's basically something that you have to choose. So I'll discuss later the jet algorithms, and there's basically algorithms that tell you how large these things are. So they're not just Gaussians. So you have to basically, you can compute these things. So the size of the cone is something that you choose, but then the distribution, given a certain size, that's something that you have to compute in perturbation theory. It's not just a Gaussian. You have to do a perturbative calculation, and then it's like some distribution that has as you would expect kind of a peak somewhere, right? And then it would fall off. So that's sort of, if you think of it, for example, in terms of the mass, right? It's like a typical mass of the jets, and then it's very likely you'll find sort of an average mass, and then it falls off toward very large values and small values, but it's not a Gaussian distribution. And the size of the jet, that's something I'll get back to in a couple of slides. That's something that depends on the jet algorithm, and there's no unique answer to this. So that's something I'll get to in the next slides.
Okay, thank you.
Thank you.
There is another question from Ruki.
Sure.
Yeah. So, if you have the event average azimuthal distribution, would you be able to say that there were jets formed?
Would I be able to say what? Say again.
The
Sorry.
jets, yeah, like in what direction the jets are formed in, like from the event averaged azimuthal distribution.
In what direction they are formed?
Yeah.
I'm not quite sure I understand the question, right? I mean, you see, if you have, I mean, if you just write it so in, so I'll introduce the coordinates later, but right, you have basically two coordinates, right? One of them is like an azimuthal angle around phi, right? Mm-hmm. And this is unpolarized scattering, right? So this will be symmetric in in azimuthal angle, right? In polar angle, there will be a distribution, right? In the rapidity that will change. But in terms of phi, right, that goes around the beam axis, that will be completely symmetric in this case, right? If you have some spin-dependent processes, right, like at the EIC or so, that can be different.
Oh, but then aren't these cones transverse to the beam?
So sorry, say again.
Aren't these cones, the cones from these jet cones, transverse to the beam direction?
Yes. So right. So the beam, right. So every single event, right, that of course is not symmetric, right? So like the beam, right, goes in this direction and the cones come out basically to the sides, right?
Yeah.
So in this particular case, right, this is basically pointing us where we would expect the quark or gluon to have originated, right? What I just meant is that like event average, right? I cannot say on a event by event, I cannot say if this is like guaranteed to be a Higgs jet, right? Like it's very likely that that's a Higgs jet, right? But if there are also other background processes that, for example, can form a heavy quark BB bar pair that will lead to a very similar signature, right? That can also basically fake a Higgs jet. And so in that sense, I cannot say, you know, on like a case by case basis, what exactly it is, right? Does that answer?
Yeah. Yes. Thank you.
But if you, right, so if you just look at these azimuthal distributions, right, around the beam axis, right, and there's no preferred direction if I average over all of the events, right, then that will average out. So there's no like asymmetry or something in this. So that's maybe what I was referring to. Yeah. Okay, thanks. Other questions? No? Okay, then let me continue. All right, so I'll talk more later about sort of the EIC perspective on, you know, what's interesting about jets and why. But to motivate again a bit historically why there was so much development in jet physics over the last 10 years, then we again go back to Higgs physics and the LHC. And also now, of course, Higgs physics is still really important, right, in high energy physics, because well, we know there's a Higgs and we know its mass and so on, but we don't really know, for example, is it a standard model Higgs, right? We don't know, like, what are the Higgs couplings? We don't know the Higgs potential, right? Like all these kind of things, right, would be super important to tell us something about physics beyond the standard model, because these standard model particles are probably going to couple to the Higgs. So the more we understand about the Higgs, the better. And so, of course, what we need to do is we need to experimentally just produce a lot of Higgs particles. And then we need to look at the experimental signatures. And ideally, we want to look at all the channels, all the possible ways we can reconstruct the Higgs. And so that's what I'm trying to illustrate here. So we start with a Higgs particle that is produced, say, at the LHC or some other future collider. And then it decays to a bunch of different particles. So of course, the Higgs also by itself is very short-lived, right? We're not going to see the Higgs in the detector, but we'll see its decay products. And then from these decay products, we have to reconstruct what will happen. And so what you can see here in this pie chart are the different particles that it decays to. So for example, it decays to 60%, or it's 60% of the Higgs particles will decay to quarks. That's sort of the blue part here on the right. And that, of course, includes also all kinds of different quarks. So it will include the light quark flavors, it will include heavy quarks. So it's not, so one can also, like, you know, make it more differential, right, and study what exactly the quarks are. Then there's about 9% of the Higgs will go to gluons. Then there's these W bosons, Z bosons, 21 and 3%. And then there's tauons as well, which is 6%. And then there's photons, which is 0.2%. And so ideally, we want to reconstruct all these things. And so the interesting thing is that, as it turns out, most of these are actually jet-like signatures in the detector, right? So we don't observe the quarks and gluons, right? So for sure, they're actually going to be jets, right? So we can group those two together. So 60% plus 9%, we have 69% of the Higgs decay products are definitely already going to just appear in the detector as a jet signal. And then, as I mentioned, right, also these other particles like a Z boson or a W boson, I have one more slide on the next one, that will actually also decay, right? We don't see the Z or the W directly, that will also decay. And it will decay in a way that it actually also produces jets. And the same thing for these tau particles. So in the end, what the Higgs does is it basically just produces a lot of jets. And actually it produces 98% jets. And there's really only 2% that are not jets in the detector. So there's these electromagnetic particles, photons, and electrons and muons. Photons are really just 0.2%, and this are 1.8%. So if we only look at the electromagnetic part of the decay spectrum of the Higgs and only reconstruct the electromagnetic particles in the detector, then we're really just making use of 2% of the cross-section. We would be neglecting 98% of the total Higgs production rate. And that's, of course, very important then to analyze these jets and try to make use of it, right? So we already found the Higgs actually with these 2%, right? The Higgs was found just with electrons and muons and photons, right? That was enough to find the Higgs, right, and get its mass. But if you want to understand more about it, as I mentioned, right, these couplings to heavy particles, to the top port, the Higgs self-interaction, things like that, right? Eventually, we should basically make use of these 98%. So by understanding jets better, right, and being able to disentangle what are these different contributions here that lead to these jet-like signatures in the final state, we should really better understand jet physics really well, and that will help us to actually understand all kinds of aspects of the Standard Model and search for physics beyond the Standard Model. And an important tool here actually to basically decompose this 98% is basically just to use machine learning. And so I'll talk about this probably tomorrow, how we can try to dissect this 98% and try to recover what are actually the particles. Because right, the problem is that what you see in the detector are really just jets. Everything looks just like the jet, right? Like everything's kind of the same. And so what we need to make use of is the substructure of jets to identify on an event average basis where those jets actually came from. Was it a quark or a gluon, and can be somehow related ideally to the Higgs particle. Okay, so here still a slide to illustrate why these gauge bosons or how they decay. They can decay in different ways. And I'm really just showing cartoons here for now, but they can decay in different, so it's really like any heavy gauge boson. So it can be, say, a W, it can be a Z, it can be a Higgs, it can be, you know, things beyond the Standard Model, like W prime and Z prime. And so it kind of depends on how they are produced. You can have, for example, a collision where these particles are basically produced at rest, right? So for example, you have an initial gluon-gluon pair and it produces a Higgs. Then the Higgs can, for example, just sit there, right, at the LHC, and that will decay. And if it decays, it will produce, say, these two jets that are shown here, right? If it's produced with at rest or very close to rest, so very low transverse momentum for the Higgs itself, right, it will decay to just two jets. And then you basically have to recover these two jets, or you measure these two jets in experiment, and that can come from a Higgs. But they're not always produced at rest, of course, right? There's a distribution in terms of the transverse momentum of, say, all these particles that are produced. Say the Higgs has a transverse momentum distribution. And if it turns out that the transverse momentum of the Higgs is sufficiently large, then these jets are going to be more close together, or they can be so close together that all the decay products are actually merged into a single jet as well. So that's also a possibility. And so if you want to reconstruct then the Higgs particle, we have to account for all of these different things, right? All the decay products can be merged into a single jet, or we have to identify two separate jets to actually recover where this is coming from. So depending on the energy of the jets, the energy of the Higgs will either get two jets or get one jet. And so the way to then look at this is to basically look at the substructure of jets, look at the radiation pattern in these jets, right? It looks more simple here and here, versus here everything's basically together. So this will have, generally speaking, like a richer substructure. And so by analyzing this, hopefully we can then recover what situation we're in. Okay. All right. So now a few words about QCD. Of course, what we want to do is to ideally predict these jet cross sections, jet substructure from first principles in QCD. And well, the Lagrangian of QCD, of course, has been known for quite some time. You can see it here. I think that was covered, I guess, on the first week of this school, where, just to recap very briefly, right, we have these quark fields in red, then we have the gluon fields over here, and in the F mu nu tensor. And so, because of the structure, we find that we have both quark-gluon interaction vertices, so that's a QED-like, and we also have gluon self-interaction vertices, right? That's something we don't have in QED. We only have that in QCD because it's a non-abelian gauge group. And so the existence of this additional vertex compared to QED leads to the fact that the coupling strength of the interaction of QCD basically becomes smaller and smaller as we go to high energies, right? So typically we then write this here in terms of alpha s, which is just gs squared over 4 pi, and then have to do renormalization and so on. But what it means, because we have these non-abelian terms here, it means that the strong coupling constant becomes very small as we go to high energies. So that's what you can see here on the right. If we're in the region of very high energies, and what is shown here is alpha s, as a function of the scale q in GeV, and this is on a log scale, so we're covering here 3 orders in magnitude from 1 GeV up to 1,000 GeV. And if at very high energies, alpha s becomes small. So that's the region of asymptotic freedom. That's what led to the Nobel Prize in 2004. And so if we talk about jets at the LHC, right, then as I mentioned before, we can be talking about scales that are up to 5 TeV, right? So 5 TeV, that's not even on, well, no, so this goes up to 2 TeV. If at 5 TeV, we're even over here, right? So it's really, really high energy. So we're in a regime where we can really hope or expect that perturbation theory works just really, really well, right? Like alpha s is small, and so even a leading order calculation should give me a relatively good approximation of the total cross section, for example, right? And so then what I can do is I can, if I'm interested in, say, any jet cross section, I can use a perturbative approach. So I have some cross section here, for example, that tells me how many jets are there in the event, what's their, say, distribution in transverse momentum or in rapidity. Then we can write down here this perturbative expansion where the leading order cross section is really dominant, and higher order terms are then suppressed by increasing powers of alpha s. So for example, the first correction here, the next leading order correction comes with 1 power of alpha s, the n analog next leading order correction comes with 2 powers in alpha s. And if alpha s is sufficiently small, say it's something here of even less than 0.1 at the LHC, then these terms can be really small, or at least they're often small. Often, there's problems with that, but that's sort of a separate problem, right, that we have to deal with later. So in general, by using jets, right, we can hope to be in a regime where perturbation theory works very well. Now, in many cases, that actually is not quite the case. There are these coefficients here can often be very large. There can be large logarithmic corrections in here, so we have to worry about those. But still, in general, we are in a regime where perturbation theory works well. And if we go then to lower energies, say we go to EIC energies, where we may be talking about jets with energies of, say, 10 GeV, so around here, then alpha s becomes larger, right? And so in that case, it'll get more difficult to do perturbative calculations. But as it turns out, it's still going to work, even though this is relatively low energies. But of course, if we push it too much, eventually we're in a regime of confinement where alpha s is large, and then perturbation theory will break down. We'll have to think about how to include systematically non-perturbative corrections as well. But generally, the main idea of jet physics is that perturbed QCD works very well, and in cases where it doesn't, then we'll have to think about how to actually include this in a systematic way to account for non-perturbative effects. But generally, that'll be the idea, to think about perturbative calculations that we can compare one-to-one to experimental results. Okay, so that was my introduction. now here's sort of an overview of different topics that I'll try to cover. I'm not quite sure how far I'm going to get, so but I'll start with sort of the basics of jet physics. So that will include things like the jet algorithm. Then we'll look at some perturbative QCD calculations for things that are relevant for inclusive jet production, exclusive jet production, and then also some jet substructure, right? We need to think about jet substructure if we want to understand, say, whether this was a Higgs jet or a quark or a gluon jet. Then there are particular issues that arise if we think about jets at the LHC. So that, and it's not just the LHC, actually, it's any PP collision or heavy ion collision, anything that has QCD particles in the initial state. So that's sort of the important difference compared to, say, E plus E minus collisions. E plus E minus collision is much harder, it's much simpler because there's no QCD radiation in the initial state. So there's specific difficulties that arise in this case. At the EIC, it's a little simpler because at least we'll have, one incoming electron and a proton or a heavy nucleus. So it's sort of half as difficult, but there's also it comes sort of with its own issues, right? That it's at very low energies. And in this case, and I'm not quite sure how much of this was covered, but in this case, you can use jets, for example, to better understand hadronization, to understand transverse momentum distributions like PDFs, to sort of try to decorrelate initial and final non-perturbative contributions. So I'll try to cover some aspects here. And as I mentioned, there's also quite a lot of effort that goes on, where people put a lot of effort into developing those tools, is in the context of machine learning. So in particular, in the case that I showed, where we try to understand, is this jet coming from a Higgs or is it coming from a quark or a gluon? Then, as it turns out, machine learning can be very powerful. The question is often how much can we trust it? So that's sort of a separate issue, but it's, I think, a very important component where I think there will be also interesting, new QCD to be learned. But what was generally found is that machine learned, say, taggers that tell us was this a quark or a gluon jet is like way better than anything, we came up with sort of as a community in sort of the perturbative QCD framework, right? Like whatever we came up with there is like much worse than, or not, I shouldn't say much worse, but it's worse than if you use machine learning. But the question is, can we really trust the machine learned results? So that's sort of a separate question, but it definitely tells us that there's some physics in there that maybe we didn't really think about before. And so then I may still cover some additional topics. Okay, are there any questions? Otherwise,
I think here is a good point to stop
Yeah.
for a break.
Right, we can do that.